Hello. Moving on to chapter 4 now, to Newton's laws of motion. Now that we know how to describe motion, we have a way to describe motion. We know some kinematics in one, two, and three dimensions in terms of the uh, position, velocity, and acceleration of objects or points, each the derivative of its predecessor. We may now address the question, what causes motion? We have description, what's the cause? Now, this is not a question of definition, but it's a question of how does the world work, actually. So we have to take it's an empirical issue. We have to make some experiments to determine what causes motion. The answer we know intuitively. What causes motion pushes and pulls, whether by people or things. It is a push or pull on a thing that causes another thing to move. Might be from a person's hand, the pull of a rope, the push of a spring, etc. Each of these we call a force. Forces cause motion. All right. But how do we formalize that? How do we put that into some kind of mathematically recognizable language? Well, we need to make there some careful observations. First, that when we eliminate forces, first thing we might notice about this, we eliminate forces. That does not necessarily eliminate a motion per se. We might have, for example, some object that we are pushing, say with our hand maybe on a table, very smooth table. We push it, give it some velocity, right? Stop pushing it if the table is very smooth, which is difficult, impossible to really attain on Earth. But on a perfectly smooth table, if there's no friction between these the contact surface, then the velocity here will be the velocity here. Although there's no force acting from here to here. So it does not take force really to cause motion it does not take force to cause velocity, put it like that. Motion is a more general term. Eliminate forces does not eliminate speed. And that's what introducing a force does. If we introduced a force, say, at this point, whether by friction or any other means, is to change the velocity. So if this part of the surface maybe were perfectly smooth, velocity here is velocity here, and now maybe it's rough, and we have introduced then at this point a force, a frictional force in this direction, and that causes the velocity to change. So that the aspect of motion that forces effect is the acceleration. It's change in velocity. The greater the force, the greater the change in velocity. So that would be something that that's an observation, and we might speculate that the net force, the total force on an object should be some kind of, maybe some power of the acceleration. Forces affect acceleration, so maybe we could try this model out and see how far it goes, or we'll test it further to see what we have. We also noticed, having come by this, we also notice, also know rather intuitively, that the more substantial the object being acted on by this force, the more resistant it is to this change in motion. The heavier the object, the more it resists this change in motion. the less the force will change its motion. And this inertia we might again initially measure by its weight, which will now let us call its mass. So in addition to this, we might try out that the proportionality constant is the mass, the measure of inertia of the object to some power. Sorry, that's like K. So these are like unknowns. A to some power, M to some power. Let us standardize these pushes and pulls, these forces. Here we can standardize those by some standard scale. Some marks on a ruler next to a spring, measuring the amount the spring is stretched. And so we can standardize our pushes and pulls, whether by a rope or a hand, a gust of wind and a sail, whatever, it being applied to this end of the spring. How far, how much does that force pull it out? That's a measure of the magnitude of that force. Standardize the force. For a single mass, then looking at this relation, if we standardize the force, then all forces in this way, and take some measurements, what will we find? We'll get some data. We plot the data, and for those, for the resulting acceleration, we find this straight line. We use our standardized forces, measure the resultant acceleration, and we see something roughly a straight line. So we find experimentally F proportional to A. So in this end here, we find it to be 1, or by the same strategy, we can standardize weights by using a vertical scale. Attach the weight to the spring and get a set of weights for these different magnitudes here. There too, we plot that data. We will plot for given force, we plot applied to different masses, we plot the acceleration as a function of 1, the inverse of that mass, and we'll find this straight line. So there too, we further refine this model and find that A is F net over M to the first power. That's i.e. we discover Newton's second law. F net being the sum of forces acting on object M having resulting with this acceleration A. Newton's seconds law.